ground fault circuit interrupter, or GFCI, is a device designed to detect small imbalances in electrical current between the hot and neutral wires of a circuit. Its primary function is to quickly interrupt the circuit's power supply when such an imbalance is detected. This rapid interruption is crucial because it prevents the flow of electricity, significantly reducing the risk of electrical shock to individuals who might come into contact with a live electrical conductor or a faulty appliance. GFCIs are commonly installed in locations where there is a heightened risk of electrical shock, such as bathrooms, kitchens, garages, and outdoor outlets. These areas are prone to moisture or direct contact with the ground, increasing the potential for current leakage and electrical hazards. Ground fault protection equipment, or GFPE, is a broader term that encompasses various devices and systems designed to protect against electrical shock resulting from ground faults. A GFCI is one specific type of GFPE, but the category includes other types of protective devices as well. Among these are ground fault equipment protection, or GFEP devices. These are designed to monitor the ground wire within an electrical system. If a fault is detected, meaning current is flowing through the ground wire when it shouldn't be, the GFEP device will trip the circuit, cutting off power and preventing potential electrical hazards. Another type of GFPE is the low voltage ground fault circuit interrupter, or LVGFCI. This is similar in function to a standard GFCI, but it is specifically designed and rated for use in low-voltage circuits. LVGFCIs are employed in applications where low voltages are used, still providing the same ground fault protection as their high-voltage counterparts. Finally, there is the residual current device, or RCD. This device measures the difference in current between the hot and neutral wires in a circuit. If the difference exceeds a certain threshold, indicating a current leakage to ground, the RCD trips the circuit, interrupting the power supply to prevent electrical shock. A key difference between a GFCI and other types of GFPE lies primarily in how they detect ground faults. A GFCI specifically measures the current imbalance between the hot and neutral wires. If the current flowing through the hot wire doesn't equal the current returning through the neutral wire, it indicates that current is leaking elsewhere, likely to ground. This imbalance triggers the GFCI to trip. Other GFPE devices, such as GFEPs, monitor the ground wire directly for any unintended current flow. If current is detected on the ground wire, it signals a ground fault, and the device trips the circuit. RCDs, like GFCIs, also measure current imbalance, but they may have different sensitivity levels and tripping characteristics depending on their design and application. Another important difference is the scope of protection offered by each type of device. GFCIs typically protect a single circuit or a specific outlet. When a GFCI trips, it only interrupts the power supply to the circuit it is installed on. On the other hand, other GFPE devices, like GFEPs, may be designed to protect multiple circuits or even an entire electrical system. These devices are often used in industrial or commercial settings to provide comprehensive ground fault protection across a larger area. GFCIs find their most common applications in residential and commercial settings. You will typically find them in bathrooms, kitchens, garages, outdoor outlets, and other areas where there is a high risk of electrical shock due to moisture or contact with the ground. GFEP devices, on the other hand, are more likely to be found in industrial, medical, and other specialized applications. These devices are used to protect sensitive equipment, prevent electrical hazards in hazardous environments, and ensure the safety of personnel working with electrical systems. Both GFCIs and other GFPE devices are essential safety components in modern electrical systems. They play a critical role in protecting individuals from electrical shock and preventing equipment damage due to ground faults. The specific type of GFPE that is most suitable for a particular application depends on several factors, including the specific requirements of the application, the level of protection needed, and the applicable electrical codes and standards. In selecting the appropriate ground fault protection, it is crucial to consider the potential hazards, the sensitivity required, and the scope of protection desired. Consulting with a qualified electrician or electrical engineer is highly recommended to ensure that the correct GFPE device is chosen and installed properly. One should understand the function of equipment grounding. The grounding conductor provides a low impedance path for fault current to return to the source. This low impedance path facilitates the operation of the overcurrent protective device such as a circuit breaker or fuse, quickly clearing the fault and preventing dangerous voltage from appearing on metal parts of equipment. The National Electrical Code, or NEC, specifies requirements for grounding and bonding electrical systems to ensure safety. Grounding and bonding create a low impedance path for fault current, helping to quickly trip over current protection devices like breakers or fuses. This prevents dangerous voltages from appearing on metal parts of equipment, reducing the risk of electric shock. Grounding electrode systems consist of various components such as ground rods, ground plates, and underground metallic water pipes. These components are connected to form a grounding electrode system that provides a connection to the earth. The NEC specifies requirements for the size and type of grounding electrodes to ensure effective grounding. Bonding is the process of connecting metallic parts of an electrical system to create a continuous electrical path. Bonding ensures that all metal parts are at the same electrical potential, reducing the risk of electric shock. The NEC specifies requirements for bonding conductors, including their size and installation methods. Now, let's delve into the differences between equipment grounding and system grounding. Equipment grounding involves connecting non-current carrying metal parts of equipment to the grounding electrode system. This provides a path for fault current to return to the source, tripping the overcurrent protection device. System grounding, on the other hand, involves grounding the neutral conductor of an electrical system. This helps to stabilize the system voltage and provides a reference point for fault current. The NEC specifies requirements for both equipment grounding and system grounding to ensure electrical safety. There are also different types of grounding systems, including grounded and ungrounded systems. Grounded systems have a neutral conductor that is intentionally connected to ground. This provides a low impedance path for fault current and helps to stabilize the system voltage. Ungrounded systems do not have a neutral conductor that is connected to ground. In an ungrounded system, a ground fault will not immediately trip the overcurrent protection device. However, it is important to note that ungrounded systems are not truly ungrounded, as there is still capacitance between the conductors and ground. This capacitance can allow a small amount of current to flow in the event of a ground fault. Now we can discuss ground fault protection for equipment. Ground fault protection for equipment, often abbreviated as GFPE, is designed to detect and interrupt ground faults in electrical equipment. GFPE is typically used on larger electrical systems, such as those found in commercial and industrial buildings. The purpose of GFPE is to reduce the risk of damage to equipment caused by ground faults. A ground fault occurs when current flows from a conductor to ground through an unintended path. This can happen if the insulation on a wire is damaged or if there is a short circuit to ground. Ground faults can cause equipment to overheat, malfunction, or even catch fire. GFPE works by monitoring the current flowing in the grounding conductor. If a ground fault occurs, current will flow in the grounding conductor. The GFPE device will detect this current and trip the circuit breaker, interrupting the flow of electricity. The NEC requires GFPE for certain types of equipment. For example, the NEC requires GFPE for service equipment rated 1000 amps or more. The NEC also requires GFPE for certain types of feeders and branch circuits. The requirements for GFPE are found in NEC section 230.95. There are different types of GFPE devices available. Some GFPE devices are designed to protect the entire electrical system, while others are designed to protect individual pieces of equipment. The type of GFPE device that is used will depend on the specific application. The selection of GFPE involves several factors. These factors include the size of the electrical system, the type of equipment being protected, and the potential hazards associated with a ground fault. It is important to consult with a qualified electrical engineer to select the appropriate GFPE device for a particular application. GFCI protection is primarily focused on personnel protection. GFCIs are designed to protect people from electric shock by detecting very small imbalances in current. GFPE, on the other hand, is primarily focused on equipment protection. GFPE is designed to protect equipment from damage caused by ground faults. GFCIs trip at a much lower current level than GFPE devices. GFCIs typically trip at a current level of 5 mA, while GFPE devices typically trip at a current level of 30 mA. This is because GFCIs are designed to protect people from electric shock, while GFPE devices are designed to protect equipment from damage. There are several important considerations for both GFCI and GFPE. For GFCI, these considerations include proper installation. GFCIs must be installed correctly in order to function properly. This includes ensuring that the GFCI is properly grounded and that the wiring is correct. Routine testing should be performed. GFCIs should be tested regularly to ensure that they are working properly. The manufacturer's instructions should be consulted for specific testing procedures. GFCI protection should be present in all required locations. The NEC specifies the locations where GFCI protection is required. These locations include bathrooms, kitchens, garages, and outdoor areas. For GFPE, these considerations include coordination with overcurrent protection. GFPE devices must be coordinated with the overcurrent protection devices in the electrical system. This ensures that the GFPE device will trip before the overcurrent protection device, protecting the equipment from damage. Selective coordination ensures that only the closest upstream protective device trips, minimizing the impact of a fault. Regular maintenance and testing of the equipment is needed. GFPE devices should be maintained and tested regularly to ensure that they are working properly. The manufacturer's instructions should be consulted for specific maintenance and testing procedures. Proper application is a consideration. GFPE devices should be applied in accordance with the NEC and other applicable standards. It is important to consult with a qualified electrical engineer to ensure that the GFPE device is properly applied. Grounding electrode conductors connect the grounding electrode to the electrical system's grounded conductor, typically the neutral. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. Bonding jumpers are used to connect metallic parts of the electrical system to ensure electrical continuity and a low impedance path for fault current. The size of the bonding jumper is determined by the size of the circuit conductors, as specified in NEC Section 250.102. Surge protection devices, or SPDs, protect electrical equipment from voltage surges caused by lightning, utility switching, and other transient events. SPD diverts surge current to ground, preventing it from damaging sensitive electronic equipment. SPD are typically installed at the service entrance and at branch panels throughout the electrical system. Transient voltage surge suppressors, or TVSS, are similar to SPD and provide protection against voltage surges. TV assist devices are typically installed at the point of use, such as at a computer or other electronic device. Harmonic filters are used to reduce harmonic distortion in electrical systems. Harmonic distortion can cause equipment to overheat, malfunction, and even fail. Harmonic filters are typically installed on the load side of nonlinear loads, such as variable frequency drives and electronic ballasts. Power factor correction capacitors are used to improve the power factor of electrical systems. Power factor is a measure of how efficiently electrical power is being used. A low power factor can cause increased energy costs and reduce system capacity. Power factor correction capacitors are typically installed on the load side of inductive loads, such as motors and transformers. Understanding electrical drawings and schematics is essential for working with electrical systems. Electrical drawings and schematics provide a visual representation of the electrical system, including the location of components, wiring, and other details. It is important to be able to read and interpret electrical drawings and schematics in order to properly install, maintain, and troubleshoot electrical systems. Different types of electrical drawings and schematics are available. Single-line diagrams show the main components of an electrical system and their interconnections without showing all of the details. Wiring diagrams show the complete wiring of an electrical system, including the location of all wires, components, and connections. Schematic diagrams use symbols to represent electrical components and their connections, providing a simplified view of the electrical circuit. Troubleshooting electrical circuits involves systematically identifying and correcting faults in electrical systems. This requires a thorough understanding of electrical principles, as well as the ability to use test equipment and interpret electrical drawings and schematics. Safety precautions are crucial when working with electricity. Always de-energize circuits before working on them, and use appropriate personal protective equipment, or PPE, such as gloves, safety glasses, and insulated tools. Follow lockout-tagout procedures to ensure that circuits are not accidentally re-energized while you are working on them. Electrical testing equipment is used to measure electrical parameters such as voltage, current, resistance, and continuity. Common types of electrical testing equipment include multimeters, clamp-on ammeters, and voltage testers. It is important to use the correct testing equipment for the task at hand and to follow the manufacturer's instructions for proper use. Electrical codes and standards provide guidelines for the safe installation and maintenance of electrical systems. The NEC is the most widely used electrical code in the United States. Other codes and standards may also apply, depending on the location and type of electrical system. It is important to be familiar with the applicable electrical codes and standards in order to ensure that electrical systems are installed and maintained safely. Electrical safety audits are conducted to identify potential hazards and ensure compliance with electrical codes and standards. Electrical safety audits are typically performed by qualified electrical inspectors or safety professionals. The results of the audit are used to develop a plan for correcting any identified deficiencies and improving electrical safety. Remember that working with electricity can be dangerous, and it is always best to consult with a qualified electrician or electrical engineer if you have any questions or concerns. The information provided here is for general educational purposes only and should not be considered a substitute for professional advice.